Well, this is lecture 32, and in 2018 here, the class is not meeting right now, so I'm making this extra video for them to watch over the next day or so, and then we're going to get back together for lecture 33 next week. We just took an exam, third exam, maybe you in a future class did as well, and I think the class in 2018 has been working really hard, and if you worked really hard, I think in studying for that exam, it's going to definitely pay dividends these last couple weeks of class for the semester. In lecture 32, the topics are going to be constructing finite fields of order p squared. Vector spaces is going to be the main topic, actually, so we're going to review linear algebra very quickly, the theoretical linear algebra. And then at the end, we'll do a field extension of the rationals as an example of what we're about to get into. Actually, the first example, constructing finite fields of order p squared, is going to be very much related to what we're going to do these last couple weeks as well. So this is our last broad topic, in-depth field theory. As much depth as we can get in 7 lectures here. Oh, and we've saved the most challenging main topic for last. Sorry about that. Well, but wait. Could it also be the most fun topic? Maybe. You might think, in spite of its difficulty, that it is the most fun. It's possible. Okay? Or if you really like group theory, maybe you'll end up thinking group theory is the most fun. If you really like factorization of polynomials, which we're still going to do, actually, well, that might have been the most fun, but I think this will play off of that enough to maybe make this more fun. So even though it's going to be challenging, it should be, in some ways, fun. I will do my best to consider lots of examples to make the theory more concrete. Very theoretical stuff as you do the reading. Look at the theorems, try to understand what their theorems say, try to understand their proofs. It's all pretty heady stuff. It's the stuff I struggled with the most when I was your age. And so, well, I'll do my best, okay? We'll try to make it concrete with examples. And don't forget, I told you this in a video, like 3 videos ago or something like that. Don't forget, basic techniques, such as polynomial long division and synthetic division, are often very helpful in this theoretical stuff. Even in the midst of these abstract concepts and theorems, it's going to be definitely helpful to think about examples and actually do the polynomial long division and or synthetic division when you divide by linear polynomials, monic, first degree. That it's going to be helpful. Are there applications of this abstract stuff? Well, depends on what you mean by applications. Do you mean applied math in the sense of real-life applications? Yeah, there are. Algebraic coding theory in chapter 31 is helpful in communications. When you're dealing with noisy transmissions of communications, it can correct any mistakes, so to speak, that there are in transmissions. Field theory, which does, of course, involve groups and ring theory, helps in understanding how to do that, how to do some error correcting codes. And if that's something that interests you, you can look at chapter 31 in our textbook, again by Joe Galois in Contemporary Abstract Algebra. We're in the 9th edition here in 2018. Probably is going to be chapter 31 in the future editions, though, too. Galois theory, don't say Galois, say Galois, okay? Think French. Galois theory, chapter 32, well, that's more pure math kind of stuff. Advanced theory of when polynomial equations are solvable by radicals, meaning like square roots and cube roots and fourth roots and that kind of thing is what we mean by solvable by radicals. Actually, Galois theory, even though it's part of field theory, involves a lot of group theory as well. In a sense, it's group theory applied to field theory, which seems kind of strange when you think about it, since fields are groups. You might say finite group, emphasize the finite group theory applied to field theory. It's pretty advanced, but pretty interesting. I hope that we can at least touch on it the last lecture or 2. Probably not get into it in a ton of depth, maybe focus on examples and what the main theorem of Galois theory says. You might say it's not so important in applied math because, you know, having formulas for roots is nice. In applied math, for real life, you know, you're usually satisfied with numerically approximating roots. So maybe it's not such a big deal for applied math, but there could be some applications that I don't know about. All right. So our first example to consider today is constructing fields of order p squared where p is a prime, as we usually reserve the letter p for primes. We know fields of order p. Okay, is ZP is a field of order p when p is prime. In fact, up to isomorphism of, ring isomorphisms, which in this case would be a field isomorphism, it's the only field of order p. But what about p squared? Is ZP squared a field? You should already know the answer. The answer is no, because p squared is not prime. It's not even an integral domain. It's going to have zero divisors. This is not a field, even when p is prime. This will have zero divisors. For example, in Z9, 3 will be a zero divisor in Z9. 3 times 3 will be 0 in Z9. And 9 is 3 squared. Okay? So, are there any fields of order p squared? Actually, you should maybe know the answer to that too. You've seen examples already of fields of order 4 and 8. 4 being 2 squared. 8 is order 2 cubed. Finite fields have orders that are powers of primes. Okay, like p squared or p cubed or p to the fourth, etc. A couple exercises in chapter 17 are a little interesting to think about here. Let p be a prime. 23a, which I'm modifying the directions a bit if you happen to look at the problem. Confirm that the number of reducible polynomials over zp, where p is a prime, of this form, that are monic, coefficient of x squared is 1, is p times p plus 1 over 2. And 24a, based on 23a, determine the number of irreducible polynomials over zp of the same kind of form. This can be certainly proved, but I want to use Mathematica to illustrate it. And also show you a Mathematica command that I think I might have shown you once, but I'm forgetting if I showed it to you for sure now. It's PolynomialMod. Can do modular arithmetic with polynomials. Just a second here. I like to have be able to change my window size here. So for example, PolynomialMod could take something like x plus 2 times x plus 3 mod 5, for example. So essentially, this is going to simplify this product in z5x. You might want to think on your own what it should give you here. You get an x squared, you get a 5x, which is 0, you get a 6, which is 1. We should get x squared plus 1 when we do this mod 5. And that is the case. Mathematica, as a standard thing, does lowest degree to highest degree here. If I combine PolynomialMod with the table command, which if you're a student here at Bethel, you've done Mathematica before, you should know what the table command does. It makes lists. If you don't know Mathematica, if you're somebody else watching this, well, I don't want to really explain it other than just show you what it does when I do what I'm about to do here. What I'm interested in doing here is, okay, let's go ahead and take the case where p is 5. Okay, so I've got the 5 there. I'm thinking about z5x here. I'd like to consider PolynomialMod applied to products like this where a and b vary from 0 to 4. 0, 1, 2, 3, or 4. Meaning a and b are coefficients in z5. Now, I'm writing this in factored form. It's going to expand it into unfactored form in each case. And by the degree 2 or 3 reducibility test for fields, it's then going to give me polynomials, quadratics in z5x that are reducible, because I'm writing them in terms of linear factors to begin with, in factored form there. This is syntax that's going to let A go from 0 to 4 in increments of 1, letting B go from 0 to 4 as well. If I enter this as is, it produces a list. That's maybe not so pleasant to look at. If I want to look at this more nicely, maybe I want to look at this in matrix form. Well, let's do table form. Table form. Showing me, this is kind of a matrix except without the parentheses, showing me the outputs for these things. And for example, the one example up here when A was 2 and B is 3, well, it occurs in 2 spots. There's x squared plus 1. That's in row 3 and that's one spot where it occurs at least. Yeah, now here too. A is 2 and B is 3. I think this is the one we're after, because this row, so to speak, corresponds to A is 0, then A is 1, then A is 2. This column corresponds to B is 0, B is 1, B is 2, B is 3. Yeah, this is A equals 2 row and B equals 3 column, because we're starting at 0. That's the same thing we got up here. So these are all the reducible polynomials of the form x squared plus ax plus b in z5x. Notice there's repeats. Again, we're considering these things for the example when p is 5. P equals 5 here. There's repeats. It's a symmetric matrix, which should make sense because if I did this in the opposite order for a particular A and a particular B, by commutativity I get the same thing. How many distinct things are there here? There's a 5 by 5 matrix, 25 entries. The distinct ones are on the main diagonal from upper left to lower right and say above it. 1, 2, 3, 4, 5, plus 1, 2, 3, 4 more is 9, plus 1, 2, 3 more is 12, plus 1, 2 more is 14, plus this one is 15. It looks like there are 1 plus 2 plus 3 plus 4 plus 5, 15 reducible polynomials, reducible, of this form over Z5. You've seen this kind of thing before. These are called triangular numbers because you can easily put elements that have those things that are sums of the first n integers into triangles like you have with the upper triangular part of this matrix or the lower triangular part. Meaning on the main diagonal and above forms a triangle. Think bowling, right? There's your bowling pins. How many of them are there? 10. 1 plus 2 plus 3 plus 4. It's a triangular number. 1 plus 2 plus 3 plus 4 plus 5 is a triangular number as well. And coming back to the problem statement, the problem says, confirm that the number of reducible polynomials is p times p plus 1 over 2. I hope this is familiar to you as the sum of the first p numbers. First p positive integers, to be more precise. This should equal 5 times 6 over 2, and it does. 5 times 6 over 2, 30 over 2, p times p plus 1 over 2. It's not a proof of this fact, but it's an illustration that it seems to be right. And we could apply it for other values of p. P equals 2, 3, 7, 11, 13. P could be any prime. We get a bigger matrix than if p was bigger than 5. So that's the number of reducible polynomials of z over zp of this form. And therefore, to determine the number of irreducible polynomials over zp of the same form, we take the total number of polynomials of this form, which would be p times p squared, and subtract this from p squared then. We're not really thinking about finite fields at the moment here, by the way, if you're wondering about that. Take p squared minus this thing and simplify. You get 1/2 p squared minus 1/2 p, which you can also write as p times p minus 1 over 2. That's going to be the number of irreducible polynomials. of this form over ZP. In the case where P is 5, that's going to be 5 times 4 over 2 is going to be 10 possible irreducible polynomials of this form over Z5. For the irreducible examples, you should know what special kind of ring these factor rings are, where you take ZPX and mod by the principal ideal generated by f of x. When f of x is irreducible, you should know from what we've done that this is going to be a field, right? This is going to be f of x is irreducible over ZP. This principal ideal is going to be maximal in this ring. So therefore, the factor ring, the quotient ring, is going to be a field. We already know that from theorems in chapter 14 and 17. How many elements do these fields have? We've thought about those kinds of things before as well. In this example, these factor rings are going to have elements that are, of course, cosets. And we've seen that because of calculations you can do in the factor ring, because f of x is quadratic, you can get away with linear coset representatives. Maybe I should write cx plus d. I mean, I could use ax plus b, but I'm kind of trying to distinguish it from thinking about that. Cx plus d plus the ideal. There's your arbitrary coset. C and D are going to vary over ZP. So this has p squared elements. This is going to be a field of order p squared. That's p squared elements. Okay? And just let's take an example. Go back to the Mathematica, just to double check that we don't pick a reducible polynomial here. If you look over this, for example, nowhere do you see the polynomial x squared plus 2x plus 3. I double check that ahead of time. Maybe I should double check again. Yeah, I don't see it anywhere. This is irreducible over Z5. And this means that in factoring, let's go ahead and write it out. But this coset is the 0 element of the factor ring. It's the same as 0 plus the ideal. It's the ideal itself, which is the 0 element of the factor ring. And this also implies, for example, that x squared can essentially be treated as negative 2x minus 3. Let's call this thing a to save a little time. X squared plus a is equal to negative 2x minus 3 plus a, which, since we're doing mod 5 arithmetic, is the same as 3x plus 2 plus a. It would also imply that, for example, x cubed plus a could be written as x times x squared plus a. You could replace the x with 3x plus 2. Get 3x squared plus 2x plus a, and then replace that x squared with another 3x plus 2. And then don't forget to do mod 5 arithmetic. 9x is going to be the same as 4x. 6 is going to be the same as 1. 6x is going to be the same as 1x. Looks like the answer here is that. X cubed effectively is the same as x plus 1. Fun, right? Okay, this is the kind of thing that I'm talking about when I talk about the fun of this. It's thinking about these examples and doing these calculations. They're strange enough to be kind of fun. At least to a mathematician, okay? I hope it's kind of fun for you. And it can help you understand the theory, okay? That's probably the more important thing, is that it can help you understand the theory. These fields have p-squared elements. Here's some new types of questions that we haven't asked before. For a given such irreducible polynomial, f of x, say this example we were just considering, does it have any zeros in the field? ZPX mod that. That's kind of a strange question to ask. It doesn't have any zeros in Z5, because if it did, it would be reducible in Z5, and you can double check that. F of 0 is 3, not 0. F of 1 is 1 plus 2 plus 3 is 6, is 1. Mod 5 is not 0. F of 2 is 4 plus 3 is 11. Mod 5 is 1, not 0. F of 4 is 16 plus 8 plus 3 is 27. Mod 5 is 2, not 0. And F, that's the last one, I guess. Yeah, F of 4. This doesn't have any zeros in Z5. Could it have a zero in the factor ring, which is a field? It is a field that we can do field operations with. Could we take an element of that field and plug it into this polynomial, and it's a root? The answer is yes, actually. It does have a root. And here is at least one of the roots. This coset is a root of this polynomial. This coset in the factor ring is Z5x mod by that principal ideal. Why? Plug it into F. What's F of x plus a? Meaning, what is x plus a? Quantity squared plus 2x plus a plus 3, which really should be thought of as 3 plus a. Right? That should make some sense that we would think of 3 here as 3 plus a. By the definition of coset multiplication and coset addition, that is that. This is x plus a added to itself, which will be 2x plus a. And this is, well, just a 3 plus a. That's, we did some coset multiplication there and coset addition there, and now we can do coset addition here. But wait a minute. A is this thing. And there's your coset representative, same coset representative as up here. We get 0. This is 0. In other words, x plus a in this field is a 0 of this polynomial. Is this field related to ZP in any way? Well, of course, in a sense, we use ZP to construct this because we're doing modic arithmetic. But there's another way it's related. It's a bigger field that contains the smaller field. How? Well, the constant polynomials, or I should say the constant, well, the cosets whose representatives can be constant polynomials correspond to elements of Z5 in this case. In other words, 0 plus a corresponds to 0 in Z5. 1 plus a corresponds to 1 in Z5. 2 plus a corresponds to 2. 3 plus a corresponds to 3. 4 plus a corresponds to 4. These are elements in the factor ring, where the representative is taken to be a constant polynomial, and these are elements in Z5 itself. There's a natural correspondence between these things. And so in that sense, you can think of this as being a bigger field that somehow contains the smaller one, at least something isomorphic to it. This collection of 5 elements would be a subfield, really, of this field, and it's isomorphic to Z5. It's going to be an important observation. All right, on to vector spaces. I'm going to have to go through this pretty quick, okay? I'd like to be done in about a half hour here. Going to have to go pretty quick. Vector spaces in 30 minutes, or a little less maybe even, because I have one more slide at the end. So hang on, buckle your seatbelt, Here we go. Background necessary for a fuller understanding of field theory. Vector spaces. What is a vector space? Well, you should have taken linear algebra. Certainly if you're here at Bethel, you've taken linear algebra before this course. In fact, it'd kind of be crazy not to take linear algebra before abstract algebra. Maybe it's been done. That would not be a good idea in general. But here we go. Assuming you've had vector spaces, we can go quick. A set V is said to be a vector space. Here's a new little wrinkle, though. Over a field F. In linear algebra, the field was taken to be the real numbers for the most part. The scalars were in the real numbers. Now, you sometimes can consider them to be complex numbers in that class. When I teach it, I don't typically think about that, but we could, without too much effort, consider these scalars to be either real numbers or complex numbers. But in general, now, we're saying it's any field. So the vectors are in V, the scalars are in a field F. You can, for the sake of your own imagination, imagine F to be the real numbers if you like. But it doesn't have to be. It can be any field. It can be the rationals. It can be the complex numbers. It can be a finite field like ZP, or even the one we just discussed there, the factoring that was a field with p squared elements 5 squared when p is 5. Those can be the coefficients, the scalars. V is an abelian group under addition. And there's a scalar multiplication that, technically speaking, you should probably call a left scalar multiplication, but we don't typically bother saying the word left. Define them, it satisfies properties. Closure, I'm talking about the scalar multiplication there. It's already an abelian group under addition, so it's already closed under addition. But we have closure with respect to scalar multiplication. We've got the distributive property for scalar slash vector multiplication over vector addition. Describing these properties in words in the book, it's in symbols. Here's what this one would mean symbolically. It means the scalar A times the sum of the two vectors V and W is the same as the sum of these two vectors, AV plus AW. That's distributive property of scalar multiplication over vector addition. There's also a distributive property of scalar slash vector multiplication over scalar addition. If you've got two scalars, A and B, in the field F that are being added, and that scalar being multiplied by the vector V, that's the same as the sum of these two vectors, AB and BV. That would be distributive property of scalar vector multiplication over scalar addition. The over is with respect to whatever is being added. These are technically different properties. There's an associativity property of scalar slash vector multiplication with respect to scalars being multiplied in F. In other words, if A and B are two scalars, the product of these two scalars in F times the vector is the same as, well, first scaling the vector by B and getting a new vector, and then scaling that by A. There's an associativity property like that holds. And one more property. The scalar 1 from the field F acts like a multiplicative identity with respect to scalar slash vector multiplication. 1V equals V for any V. We're not assuming that the vector space is a ring. Okay? It's just an abelian group, and we've got the scalar multiplication. There's not necessarily a multiplication of vectors going on. There could be, but we're not assuming that, and in general, there is not one. So this is not a ring thing. This is not a ring multiplication. It's scalar slash vector multiplication. To be a bit more technical, what's really going on here is we got a vector addition as a binary operation, which really means it's a function from V cross V to itself. This thing being the Cartesian product of V with itself, the set of all ordered pairs whose entries or components are elements of V. It's a function, take that ordered pair and map it to this thing we're calling V plus W, and closure is assumed when you say binary operation. So this is an element of capital V. And scalar vector multiplication is, well, I'm calling it a pseudo question mark binary operation. Why do I call it pseudo? Well, it's because the domain of this function is not V cross V, it's F cross V. Ordered pairs whose first entry is from the field and whose second entry is a vector from the vector space. Take an ordered pair like that and map it to something in the vector space, and here again we are still applying closure. Binary operation can just mean two things coming together to give you a new thing, and in that sense this is still a binary operation. But I'm calling it pseudo because, well, it's a little different than this kind. Here are some basic properties of vector spaces that are actually not mentioned in the text, at least on my first read through. I didn't remember seeing them. Maybe I missed one or two. If you look in your linear algebra book, you will see those properties there. The scalar 0 times the vector v is equal to the 0 vector. Notice the boldface for the 0 vector for all vectors v and capital V. I used the boldface for the 0 vector for extra clarity. It's really not necessary, and in fact, our book probably would not do it. Most linear algebra books use boldface for vectors. In this textbook, abstract algebra, we just sort of do away with that. We know something's a vector because we say it's a vector. Okay? It would be implicitly assumed, maybe even, that v is a vector here, and that this vector would be and that this thing would be the 0 from the field f, the scalar field f, and this would be the 0 vector. 0, the additive identity of v as an abelian group under addition. They are technically different zeros. But you would hope these things would be true, and they are true. You take an arbitrary scalar times the 0 vector, you get the 0 vector for any scalar a in the field. The additive inverse of a vector is the same as the additive inverse of the unity 1 of the field times the vector. These things do take proof, and the proofs are not too hard. You should try them on your own. There's sort of a couple properties that you might call no zero divisors. You got the product of a scalar and a vector being 0, and the scalar is not 0. That would imply the vector must be the 0 vector. If you got the product of a scalar and a vector being the 0 vector, and the vector is not the 0 vector, then the scalar must be 0. So you could sort of think of this as saying no zero divisors, but we don't typically say that. That's reserved for rings. We say, well, we've got a 0 divisor. There's a subgroup test. There's a subring test. I suppose there should be a vector space test, but we just call it subspace test for short. But what is a subspace, first of all? Let V be a vector space over a field F. Let U be a subset of V. We say U is a subspace of V. If U is also a vector space over F under the same operations of V, meaning under the vector addition in V, but also the scalar multiplication with the scalars coming from F. We still have closure under scalar multiplication. There is a subspace test. It's exercise number 2 in chapter 19. A non-empty subset U of a vector space over a field is a subspace of a vector space if it's closed under both addition and scalar multiplication, is what this is saying essentially. Okay? That's what I hope you would guess would be the case. If you had to think about it and make a guess as to what the subspace test might look like. And yeah, actually, if you have linear algebra, you should have seen this before. You should, as usual with the subgroup test and the subring test, verify that the set is non-empty to begin with. And usually it's good enough just to observe 0 is in the set. And in our linear algebra book by David Lay, in fact, that's even the first part, I think, of the subspace test, is to verify that 0 is in the set. You're still with me? Right? You buckled your seatbelt, and so you're not falling off the roller coaster here. Continuing to go fast. Yep, pause the video if you feel like you need to stop and think. All right? I'm going to look at some examples. These are kind of abstract examples, but we'll look at a numerical example here in a minute. The kernel, or null space, of a linear transformation is a subspace. What's a linear transformation? A linear transformation, I'm not going to write it down or give you a slide with the definition, but it should make sense that you would want it to be, well, maybe you remember it's a homomorphism essentially. Excuse me. It's really a group homomorphism that is also operation preserving with respect to scalar multiplication. Not only does T of U plus V, I'm going to go ahead and use vector symbols here. Maybe I shouldn't. Okay, the book does make the convention of using letters like U, V, W to represent vectors and letters like A, B, and C to represent scalars. This is what it would mean for it to be a group homomorphism. For T to be
a group homomorphism. To be operation preserving with respect to scalar multiplication means essentially you can factor scalars out like this. So these are the two key properties that you need for a function t to be a linear transformation, which means it's a group homomorphism, thinking of v as a group under addition, but also preserves scalar multiplication. You can factor scalars out, so to speak. And if it's one-to-one and onto, you could say it's an isomorphism as well. A linear transformation that's one-to-one and onto could be called a vector space isomorphism. You might remember from linear algebra, this is often represented by a matrix times a vector as far as the formula for the linear transformation. We'll look at an example. From Rn to Rm, that would be the domain, here would be the codomain. This is n-dimensional Euclidean space, this is m-dimensional. You could think of the elements as being ordered n tuples over here, if you like. Ordered lists of n elements from R, the real numbers. That would be, you'd call it a row vector. You could also think of it as a column vector, if you like. In fact, we will do so here in a minute. Think of them as being n entries arranged as a column rather than a row. The kernel is a subspace of Rn. And what is the kernel? It's everything that gets mapped to 0, just like you would guess. Same as I give a kernel for a ring, except now we're saying the 0 element is the 0 vector, vector space. The image of a linear transformation, also called the column space. The words null space and column space often refer to the matrix itself. From Rn to Rm is a subspace of the codomain Rn. Here's a real important example using real familiar kind of notation. Let this set, with these pointy brackets in our book's notation, some books use parentheses here, but that does get a little extra confusing in this context, be the set of all linear combinations of these vectors. What's a linear combination? You should remember that, I hope. You got these vectors v1 through vn, and you got scalars a1 through an. Here is an arbitrary linear combination of the vectors. The set of all possible linear combinations like that for all possible scalars a in F, each of these ai's is in the field. If F was the set of real numbers, these ai's would be real numbers. Is denoted by this. It's a subspace of V, called the subspace spanned by these vectors. Ah, span, right? Is that a word that gives you nightmares from when you took linear algebra? Span. There's more such words to come. Subspace span. This is the sometimes alternative notation that's used is even using the word span. In our linear algebra book, this in fact is done. Span v1, v2 through vn. That notation is used instead of this, but it means the same thing. That turns out to be a subspace of V. And in fact, you could also, in analogy with what we've seen before, say it's the smallest subspace of V containing these n vectors. Actually, the list of vectors doesn't have to be finite. It could be an infinite list, but we're considering a finite list here. Here's an example involving a matrix. Consider the following 2 by 3 matrix, 2 rows and 3 columns, this one right here. I don't know why there's a little gap in my parentheses there. I think it's probably the typesetting and going from my Mac to the PC here. There's a matrix. I hope you recall that, here's another nightmare word, after a basis has been specified, typically the standard basis, the following is a linear transformation, this. T from R3 to R2 defined by T of V equals A times V, where we represent V as a column vector in R3. So A times V, if you write V as a column vector, say x, y, z, you'd write it like this. That's B. Yeah, a 2 by 3 matrix needs to be multiplied by something with 3 rows. 2 by 3 matrix, when you multiply it times another matrix, that matrix has to have 3 rows. You can have an arbitrary number of columns. Column vectors have 1 column. The answer is going to be a 2 by 1 matrix, which is a 2-dimensional column vector. By the definition of matrix multiplication, in this case, what you're going to get, I hope you recall, you're going to get that for the first entry of the image and this for the second entry. And this function defines a linear transformation. Come back over here. T is the function name. A is a matrix. T of V equals A times V. But by linearity of matrix multiplication, which you have to verify with matrices, this does end up being operation preserving with respect to both addition and scalar multiplication. You can ask questions about this like what's the kernel and what's the image? What's the null space of A? What's the column space of A? And that ends up, at least for the null space, being something you want to use row operations for. You know, you're thinking with the null space, the kernel, you're thinking about, maybe I shouldn't erase that, you're thinking about solutions of this kind of equation where this again is x, y, z, and this is the 0 vector in R2, 0, 0, 2 equations, 2 unknowns, 2 homogeneous equations, and 2 unknowns. And row operations can help you find your general solution, and sometimes you put a 0, 0 over there. Those are the right-hand sides of the equations corresponding to the zeros over there. For example, we can multiply the first row by 4 and add it to the second one to get a 0 right there. 4 times 1 is 4, plus negative 4 is 0. 4 times negative 2 is negative 8, plus 3 is negative 5. 4 times 3 is 12, plus 2 is 14. 4 times 0 is 0, plus 0 is 0. The vertical dash line doesn't have to be in there, but I like putting it in there to emphasize that the things to the right are coefficients on the right-hand side. Then you typically try to get a 1 in this spot. Got to divide the second row by negative 5. I get negative 14/5 and 0 still. One more step here. Now multiply the second row by 2 and add it to the first row to get a 0 right there. Second row is going to stay as is. Only work to do is to figure out that entry. Multiply by 2, negative 28/5 plus 3, which is 15/5, is going to be negative 13/5. And so your solution set for the system of equations can be written as x equals, x minus 13/5 z equals 0, or x equals 13/5 z. And then y minus 14/5 z equals 0, so y equals 14/5 z. And then you can sometimes write your solution as a vector, 13/5 z, 14/5 z, and z, where z is sometimes called a free variable. If you like, you can factor the z out. Z can be anything, so it makes good sense to call it a free variable. And really then, the kernel of this linear transformation, or the null space of the matrix, is the subspace of R3 spanned by that one vector, which is going to be a line through the origin in R3. And subspaces in Rn are going to be lines or planes or higher dimensional versions of those things through the origin. And I probably shouldn't really attempt to draw it accurately, but it's a line through the origin. Okay, that will be the kernel of the linear transformation, also called the null space of the matrix. What about the column space of the matrix, also called the image of the linear transformation? It would be the sum of all outputs of the linear transformation. It would be the span of these 3 column vectors. That's why it's called the column space of the matrix. Sum of all linear combinations of those things. And those things would span all of R2. The image here is going to be all of R2. This linear transformation is going to be onto. It's not one-to-one because the kernel is not trivial, but it is onto. Turns out because there are two pivot columns, you can also get away with just two of these three. Say the first two, actually any two of them will do as a basis for the column space. Come to the idea of basis in a minute here. But before that, more nightmare words. Linear dependence, linear independence. I really have to go fast now. I got about 7 minutes for my goal here. Take a breath. A set S of vectors in a vector space is said to be linearly dependent over the field F if there's some non-trivial linear combination of them that equals the zero vector. Those A's are not all zero. Extra emphasis there. If the set is not linearly dependent, it's called linearly independent over the field. So, a set forms a linearly dependent set if this equation, where that's the zero vector, has a non-trivial solution for the unknowns that are the A's. Whereas the set is linearly independent if the equation has only the trivial solution. All the A's have to be zero. These three column vectors form a linearly dependent set. Okay? You can come up with a linear combination, a non-trivial linear combination of them that equals zero. And in fact, the kernel helps you decide what to use for the coefficients. You could, for example, use 13/5, 14/5, and 1 for the coefficients, the field coefficients, scalars. In front of those column vectors, add them up in a linear combination. You should check. You would get the zero vector. You could also use any non-zero multiple of this, like 13, 14, 5. These three things would form a linearly dependent set, which is not surprising since this is two-dimensional and you've got three vectors there. Any two of these is going to be linearly independent, effectively, because no two of these is a scalar multiple of the other. Okay. What is a basis and what is the dimension? A set B is a basis for B if B is a linearly independent set over F and every element of V is a linear combination of the elements of B, where the coefficients are from F, the scalars are from F. Basis. Linearly independent spanning set for the given vector space. Turns out that these conditions actually imply every element of V is a unique linear combination of the elements of B. So it's better than just a linear combination, it's a unique linear combination. And this also justifies the use of what are called coordinate vectors for the vector space V over the field F. More about that in a minute here. There's a theorem, very important theorem, that says if you've got two bases of the same vector space that both happen to be finite, then they have to have the same number of elements. And this justifies the definition that in such a situation, the dimension of the vector space would be the number of elements in a basis. A vector space that has a basis consisting of n elements is said to have dimension n, to be n-dimensional. And it is also then finite dimensional, because n would be a finite number. By definition, the dimension of the trivial vector space is taken to be 0. And the trivial vector space does not have a basis. Which I think the book says take the empty set to be the basis, but that gets a bit confusing. So don't worry about it, just take the 0 vector space, the trivial one, to have dimension 0. There are vector spaces with no finite bases, and when that's the case, you call those infinite dimensional. The set of all polynomials of arbitrarily high degree under polynomial addition and scalar multiplication of those polynomials, say with real coefficients and real scalars, is infinite dimensional, for example. So other worthwhile facts to know, these are in the exercises, which are completion problems. If you've got a linearly dependent set of vectors, then one of these vectors is a linear combination of the other, and that's helpful to know. Every spanning collection contains a basis. If this collection spans a vector space, then some subset of it is a basis. The given set may not be a linearly independent set, and so may not be a basis. You can take vectors out until you get to a basis, until you get to a linearly independent spanning set. Every independent set is contained in some basis, if V is finite dimensional at least. If V is finite dimensional and you've got a linearly independent set, you can add more vectors to it until you get a set that spans the vector space as well as being linearly independent and is therefore a basis. And this is getting back to the coordinate vector idea here, exercise 31. If V is a vector space over the field F of dimension n, then V is isomorphic. There's a linear transformation that's one-to-one and onto from V to this set, Fn, the set of all n tuples whose entries are from F, where the operations are component-wise addition and scalar multiplication by scalars from F, where it's component-wise scalar multiplication, and the multiplication that's done is actually the ring multiplication in F. So the scalar multiplication there corresponds to the ring multiplication. In order to set up the isomorphism, you have to have what's called an ordered basis. I probably will talk about that briefly next lecture. For the moment, if you'd like to think about it, you can also look in your linear algebra book and you'll see ideas related to these things. Last slide here. Go through this quick too. The first example we did in this lecture, we created a bigger field that contained the smaller field, at least up to isomorphism. The smaller field was a subfield of the bigger one. The bigger one was a field extension of the smaller one. Talk about subfields, but we can also talk about bigger fields, field extensions of a given field. And here's one of the most common extensions of the rationals to think about. Q is a field. Recall that the following is a field. Q adjoins square root of 2. As a set, it's the set of all numbers, a plus b times root 2, where a and b are rational. I never proved this was a field. The book doesn't fully prove it, but does justify, I think, by calculations that everything like this does have a multiplicative inverse of this form. That's the main difficult thing to prove. This does turn out to be a field. The field of rationals adjoined with square root of 2, which contains more than just the square root of 2 as something that's not rational. And there it contains things like 2 plus 7 root 2, which is also not rational in this field. A few more comments about this. The second field, this one, contains the first one. Q is a subfield of this. This field is a field extension of Q. Take the b's to be 0. And you effectively get Q. It's a field extension of the first. It turns out the second field, here's where the linear algebra comes into play. The second field is a vector space over the first field. Certainly you can add things like this to things like that, and you get something like that. It's closed under addition. If you think of rational numbers as being scalars, multiply a rational number times this really irrational number in general, you still do get something of this form, because a and b times, say, c, an arbitrary rational number, is still rational. This forms a vector space over that. We're kind of ignoring the ring multiplication when we say that, but it does. And that's a really important thing for field theory. You might wonder, what is a basis and what's the dimension? This is my final comment. Maybe you want to pause the video and think about this before I say the answer. A basis for this vector space over that field consists of the numbers 1, comma, square root of 2, and therefore this field, this vector space, excuse me, is two-dimensional, because you've got a basis with 2 elements. This thing, this set as a vector space over this field is two-dimensional. And this is the simplest example of a basis. You might call it the standard basis in this situation. All right? Thanks for paying attention. More on this in the next lecture.